So what we're going to do in this PowerPoint is we're going to talk about our second group of rocks, and that is sedimentary rocks. So what we're going to cover in this PowerPoint is not just the rocks themselves, but we're going to talk a little bit about weathering. So weathering is the process of taking existing rock that's on the surface of the earth, and we're going to break it down. So one of the definitions of a sedimentary rock is that it's made of pieces of pre-existing rock that have been glued together, cemented together. And so we want to talk about how do we get the pieces in the first place. So we'll talk a little bit about weathering during this PowerPoint. Then we'll talk a little bit about some features that are preserved in sedimentary rocks, like fossils and things like that, that give us some additional information, because even though, for this class, we're doing a speed version of the different rocks, we still want to know a little bit about what the rocks tell us. And one of the ways we can do that is by looking at some of these features that are preserved in sedimentary rock. So we're going to take a quick look at that, and then we're going to name the rocks. How do we do that? So the main type that we talked about is what's called clastic, made of pieces. There are chemical sedimentary rocks, and of course, those are made of different chemicals, different minerals that we've kind of learned in the last module. So we want to look at those two types, two categories. And then we're going to use the chart like we've done for igneous rocks, and we'll use the chart to figure out what to name it. And then we'll, figure out some properties of these rocks. And of course, that can come into our kind of hazards. So rocks that dissolve with water, that's not good, right? We wouldn't want to build a dam against that. And rocks that allow water to permeate through, not good. Stronger rocks, this is what we want. So when we look at hazards, sometimes certainly we want to know rock strength and some properties of the rocks, because that helps us determine if it's a hazardous area, number one, and how it might behave in a hazard. So that's what we're going to do for this PowerPoint. So go ahead and get started.
All right, let's see how we do with our next group of rocks called sedimentary rocks. So we're going to introduce a couple topics here. One is weathering, and the second would be the rocks themselves. So in order to get our sedimentary rocks, one way we can create those is we need pieces. And so weathering is a process by which we can get those pieces. And so when we look at weathering, we want to break it down into a couple different groups. We're going to break down the first one into mechanical weathering. And this is something that's like physically cracking or breaking the rock. And then the second category would be our chemical weathering, which is some reaction process that's happening between some fluids and the rock itself that's causing it to break down. And so we also throw out a couple terms. Weathering is one, and erosion is the other. A lot of times they're used interchangeably, but technically erosion is the removal of the material that has been weathered by wind, water, or ice. And so they're not necessarily interchangeable. It's not the end of the world if we kind of go back and forth. But weathering is taking the rock and altering it in its current position, and then those fragments and pieces are moved by the process of erosion. And so one of the things that happens certainly when we mechanically break down things is we make big things into small things, which can be useful for a variety of reasons. Certainly it helps transport of the material be easier, and also it facilitates the chemical erosion that's going to take place. And so the more surface area, which is what this diagram is trying to represent, the more chemical weathering that can happen. So as we break down mechanically the rocks, the chemical processes are enhanced because they have more surface area to attack, and then they can proceed in breaking down the rocks even smaller. And so some of the mechanical weathering processes, which we'll run through really fast, are what's called freeze-thaw or frost action. And this is the idea that water, of course, is a big driver here. As the water gets onto the rocks and falls into small cracks or fractures, if the temperature drops below freezing, the water, of course, freezes, and it actually expands when it freezes. So now, I get it, it's not expanding in such a way that it's, instantly busting up all the big rocks into small pieces, but it's a time thing. The idea is that there's some stress placed on the rock by the pressure of the increased size of the ice, and then, of course, it might, get warmer, and then the ice would turn back to water, and then cold, it would freeze again. So it's kind of this back and forth motion where you have pressure, release of pressure, pressure, release of pressure. And the idea is that if we do this for long enough, and we don't talk about time too much in this class, but time is really the big factor here. If I do that every day for a year, or 5 years, or 10 years, or 100 years, over time that pressure can cause the rocks to fail, break, increase the size of the crack. Then I can get more water in there, of course, and then I can keep that process going. And then if it's an unstable piece, gravity is also pulling down on these rocks, and then they can fail and move down slope, break into even smaller pieces, and those pieces can be transported away. So I get it here in Arizona. Well, at least here in the valley, we don't have this frost action going on too much. Certainly up north that can happen, and in lots of places where there's temperatures that fall below freezing. Another mechanical weathering process called thermal expansion contraction, and this certainly happens here. And the idea is that as we heat up the rocks, they heat and cool, and the same thing is occurring when I'm heating up rocks. Remember, our rocks are composed of multiple types of minerals a lot. So let's say we take a granite. It's composed of quartz and feldspars and micas, each with different properties because they have a different chemical composition. And so they react differently to the heat. So some might expand more than others. And because these crystals are touching each other, there's some force applied to that contact between the crystals. And so as it swells a little from the heat, there's some pressure there. And then it shrinks, and back and forth and back and forth. And it's this idea of time. If we do this enough, it can cause a weakness to form, and eventually a fracture could appear in the contact between those two pieces. And then, now that that's a space, I can get some water in there, and that can cause some issues. Chemical weathering processes can occur in that fracture and then increase it. And so that whole system of mechanical and chemical working together can allow these rocks to be broken into smaller pieces, another mechanical weathering process. Okay, let's see what else I got for you. Something called exfoliation or pressure release. So it might sound a little weird, but hopefully this image on the left is a good picture to help you understand what's going on. So the explanation here is that this term batholith, remember, it relates to a igneous rock that cooled at depth. And the argument is that there are processes that uplift the land surface, which can cause the material that's above the batholith to be weathered away and expose the batholith to the surface. But of course the batholith was created miles or kilometers deep under lots of pressure. And as that pressure is released, this object expands a little bit. And it's another kind of time process, of course, because it takes a long time for this to happen. But the expansion process is putting stress on the rock. And as more material is released and there's more pressure pulling the rocks apart, they start to fracture and crack. So when they get to the surface, they have these fractures and cracks, which of course then can be exploited by other processes. But it's this big pressure release that's causing this fracture pattern to occur. In this case, this would be an igneous rock that was buried at depth. But rocks that are formed deep in the earth and then are brought to the surface through uplift and erosion would undergo this process. So some more imagery of how that might look. So all these are factors of this pressure release. Another way that we can break the rocks mechanically, of course, is organisms. Sounds weird, but we can have roots from plants that actually grow into the rock. We've seen that here in Arizona, not a lot of soil. And so, of course, they're pushing and growing. Same thing. It's a time thing, a lot of pressure. We can start to crack the rocks, make them, those fractures a little bigger. And then once again, other processes can work on that. Even burrowing animals can burrow into the rock and cause fractures and cracks to expand. And so those are kind of the main ones that we would talk about. We've got the freeze-thaw, the frost action. We've got the expansion and contraction from heat. We've got the roots, and then we've got that pressure release. Those are the main mechanical weathering processes that we want to talk about. And of course, all of these are just increasing the surface area, which allows our chemical weathering processes to take over. And so Here we're seeing that some rocks are reacting to some of the fluids that are available, and of course water is the main one that we have here. And because our water is not pH balanced, it's not neutral, because there's CO2 in the atmosphere, we can get water and CO2 to make a carbonic acid. Now, of course, it's not like it burns you as it hits your skin, because it's only slightly acidic, but it has the ability to degrade some particular minerals and rocks. So one thing it can do is it can degrade these feldspars, which are common minerals in granites and things like that. And so even just water over time on these minerals will start to dissolve them. The other common thing that we see is calcite, so another mineral that reacts to this acidic solution. And so one of the key points here about sedimentary rocks is that limestone is a very common sedimentary rock, and it's all over the place, and it's made up of calcite. And so it has the same properties of calcite, so it also dissolves in this acid. And a test that geologists use to determine if a rock, or if we have the mineral calcite, is to use a very dilute hydrochloric acid solution, put a little drop on there. If we were in real life lab, we would be doing that activity to identify calcite or limestone. And when it fizzes and bubbles, it's an indication that we do have calcite there. And that would be the mineral, and of course the rock is the limestone. And so this happens naturally because we talked about that rainwater can be slightly acidic. And so over time, this process is dissolving these rocks and minerals that are exposed at the surface or even under the ground where water can flow. We do get another chemical process called oxidation. And so that's this idea that a pyroxene, which is another common rock-forming mineral, is silicate, right, can break down and release some iron, which then reacts with oxygen, hence the word oxidation. And we get this iron oxide called hematite, a mineral. It's very red typically, and you can see that a lot of times when you look at rocks and they're very red, it's an indication that there's some iron oxide in the rock. And so when you look at the rocks of Sedona, it's really the red rocks are there because of oxidation that's happened, and there's some iron oxide or hematite in those rocks. Okay, and so when we talk about things that weather, I just thought I'd throw this up here really fast. So you can see that some stable and unstable minerals. Here we have, quartz, super stable. It doesn't weather very fast. It doesn't react with water very much. It's very strong. So on the hardness scale, it's at 7, so it's pretty hard. But these other things, calcite, this is our limestone rock, halite, these are salts and things like that. Those weather extremely quickly. And so if we took a typical granite, which had these minerals in it, and you weathered it over long periods of time, you really end up with lots of quartz. And so this is why there's lots of quartz sand everywhere, and especially potentially at beaches, because all that material is being transported through rivers, wind, and things like that from high areas, mountains and things like that, down streams and valleys. They end up in the ocean, and of course they dump all that quartz sand right at the coast, and hence we get lots of sand or quartz sand at the beach. Okay, so speaking of that, when we take our weathering processes or weathering pieces and we're moving them, they can be dumped in lots of places, and this is kind of an example of a bunch of places they can be dumped. So they can be close to the source, and we're going to argue that the source is the mountain range that you see in this diagram up here. And so we can have material that's dumped very close to the source on the continent. We can have things that are dumped a little farther away from the source on the continent, in lakes and river channels and things like that. We can dump some at the coastline here and our beaches. We can create or dump material here in the shallow marine, and we can create or dump things here in the deep marine. So these are kind of the areas where we're going to take our sediment and deposit it, and then we're going to turn it into a sedimentary rock. And so what I wanted to do really fast is, like we talk about for this class, is the focus isn't on the physical geology as much as 101. So in 101 we go through all these other things that can be found in sedimentary rocks. And so obviously we're talking about pieces. For sedimentary rock is one way we can get sedimentary rock. We take a rock, we break it down, get all these pieces. We're actually going to glue them together, and that's going to be our sedimentary rock. There's other features that get recorded in our sedimentary rock. One of the things that you see a lot is something called bedding. And so it's this layering that you see. So if you see rocks in the Grand Canyon or pictures like this or this is a layering process that's caused by the deposition of those pieces. So we break them and then we transport them. And when they get transported and then finally they get dumped somewhere, they basically pile up into these layers like this. So it's an indication of deposition. So this is very common in sedimentary rocks. We get this bedding. Now there's other features I talked about that you can get in sedimentary rocks that tell us the environment. Where was this rock deposited? What was this environment like? Look, all rocks tell a story. They're all telling us something about their history. In this class, this is not the kind of the end goal to talk about maybe the history of that, except when it kind of relates to maybe a flood or a landslide or something like that. So I don't want to get into all the details, but it's hard not to talk about these things when we're talking about sed rocks. So I'm going to just list them right here through some slides, but I don't want you to focus on this. This is not the focus of the class right now. So we get bedding we talked about. So it's just some images of bedding. You can get some unusual bedding where there's big pieces to small pieces. That gives us a clue about something that happened to this rock, or at least these pieces before it was turned into a rock. All right. And so we can look at that. This is just an illustration of how graded beds might form. This is an indicator that suggests this was a big flood. And so one of the things we'll talk about is that rounded pieces is a good indication of water, because the argument is that when things break, they're pretty angular. And as they are transported or moved, they become more rounded as they move farther from the source. And usually something that moves material long distances is water, so that's something that we would talk about for rounding indicates water transportation. But the fact that there's these huge pieces and then it changes to small tells me high velocity. I need a lot of energy to move these big pieces, but then the velocity slowed down. So we might have a place where there's a huge deluge of water come rushing down and then slowly it dissipated and it left this big huge hunk of deposit here. Other things that can tell us about the environment is some of these ripples can be preserved in the rock record, telling us where this material was deposited. So like deserts or things like that. We get some weird internal structures called cross beds. We get mud cracks, another indicator of the type of environment that this material was deposited in. We can even get some fossils that are preserved in sedimentary rocks, which can tell us something about the environment where these pieces were deposited. Okay, and then some of the locations where these things get deposited. So we would take all this information, the size of the pieces, what they look like, you know, how big and small they are, how rounded they are, all this information and all those other pieces, and try to say, oh yeah, this is the environment of deposition based on the information I gathered from the rock. So close to the source, something like this called an alluvial fan is a possible depositional environment. Just some more images of that. Because it's close to the source, they're pretty big, they're pretty angular, they haven't had time to round and get smaller as they're moved away from the source, right? Other things we might see, rivers, we can deposit lots of stuff here. We can get anything from sands, gravels, muds. Those can be deposited. Over time they build up as layers. They can be turned into sedimentary rocks. So rivers are a great place to deposit all kinds of sized sediment, giving us multiple types of rocks that would exist here. We also have deserts. Lots of sand here, certainly. And so over time, same thing. We deposit the sand, it builds up, and we bury it. We can glue those sand pieces together, end up with some sandstones. We have places where there's high evaporation rates. This is where we're making gypsums and salt deposits and things like that. And so we can get evaporites. We can also get some mudstones here. In deltas, when we get close to rivers emptying into the ocean, we get lots of muds here, really far from the source, so not much gravel here. And so we get lots of fine-grained deposits here. Same thing, they build up over time. and then we can layer them, eventually turn them into different rock types. The marines are where we're going to get our limestones, and so most of the stuff here is carbonate sediment, which means calcium carbonate. A big source for that is coral reefs, which are made of calcium carbonate, and all the shells in the ocean, which are made of calcium carbonate. As those things are broken down and destroyed, then they create this source of carbon. It can once again be layered and buried and turned into, in this case, would be a limestone. And then in the very deep marine, where there isn't a whole lot of material, we actually get some quartz deposits, silica, because of the type of creatures that exist there. And so those can build up over time and give us some rocks that are very silica rich. Okay, so remember, that stuff I just blazed through, I don't want you to focus on that, but I just want you to be aware when we talk about sedimentary rocks, environment of deposition is important, and these other features that show up in the sedimentary rock can tell us the story about that. But for now, we want to just be able to understand, how do we classify these rocks? How do we name them? And then, of course, in some cases, we're going to relate specific sedimentary rocks to some of the hazards we'll talk about in the future. But the general story for what we're going to call clastic sedimentary rocks, so rocks that are made of pieces, is that we take those pieces and we transport them somewhere. They move some distance from the source, and then they get deposited there. They get dumped there. And so over time, we continually dump more and more material. So we have deposition, then compaction from the overlying material that keeps getting added there, squishing it down. And then as water moves through these spaces here, we get the formation of sediment here. And so the sediment typically is calcium carbonate or some type of silica, SiO2 quartz. And so that is what's holding these pieces together. The cementation then will turn it into a sedimentary rock. So we end up with the lithification process is deposition, compaction, and cementation. That's taking pieces and turning them into a clastic sedimentary rock. So we're talking about the category of clastic sedimentary rocks. We're talking about pieces. That's what a clast is. And so one of the ways we identify the rock types is based on the size. And so here's an indication of some sizes here. But these terms that you see, gravel, sand, and mud, are actually size designations in geology. Okay, and so the first thing you want to do when you look at a sedimentary rock is determine, is it made of pieces or not? Because our two main categories are going to be, yes, we're going to call that rock a clastic sedimentary rock. If we don't see any pieces, or we're not sure there's any pieces there, we're going to call it a chemical or a biochemical rock. And so there's two different ways to identify those. For the clastic, we want to know how big the pieces are in general. And so for us, we're going to use kind of this designation. So we're just going to say they're either gravel size if they're bigger than 2 millimeters, they're sand size if they're between 2 millimeters and 1/16, and they're mud size if they're any smaller than that. And so if I said how big are these pieces and they're bigger than 2 millimeters, you'd say they're gravel size pieces. So look, 2 millimeters, I know you might not know that off the top of your head, but sand, kind of like, think about beach sand. That falls into the 2 millimeter to 1/16 of millimeter size. And anything bigger than that, we're going to call gravel. And remember, all of the pieces don't have to be greater than 2 millimeters. As long as there's one piece bigger than 2 millimeters, then there's gravel-sized pieces in there. And we're going to use that to help name this clastic sedimentary rock. The other way we're going to name a clastic sedimentary rock is how well-rounded the pieces are. So when they're big enough to see with your naked eye, you can make the call whether they're either angular, so they have sharp edges, or they're rounded. Remember, this is an indication of distance traveled. So the farther pieces travel, the more bouncing and rolling they're doing, so the more rounded their edges are. And we did also argue that rounding is a good indication that water was the mover of these pieces. Sorting is another way we can identify what type of clastic sedimentary rock we have. And so all that means is that they all look the same size. If there's a bunch of different sizes, it's poorly sorted. If they're all the same, it's very well sorted. And so that can, another thing, distance from source should sort out these big pieces and break them down. So that's an indication of how far away these pieces moved. And there's some other indications there, but we'll go into that later if we need to. And then class composition can tell us something, but we're not going to focus on that too much. But what the pieces are made of can also tell us something about the history of the sediments that make up our rock here. So here's the story. We've got our kind of basic sedimentary clastic rocks, and we're going to name them using this chart here. I'll go back to that in just a second. But if you look at this chart, just like for igneous rocks we had a chart, the clastic rocks are just these four right here. There's a breccia, a conglomerate, a sandstone, and a mudstone. We could also call it a shale. But it's based on this size designation that I showed you earlier. If there's any pieces that are greater than 2 millimeters, it's got to be one of these two. How do we know the difference? Well, we look at the rounding. If it's angular, it's a breccia. If it's rounded, it's a conglomerate. And so the angular indicates that probably water wasn't involved in moving it and it's close to a source. This could be an indication of like a landslide deposit. The conglomerate suggests that it moved a little farther from the source. Then, of course, sandstone and mudstones, we get smaller and smaller. When they're really small and we can't even see them with a little magnifying glass, we're going to assume that they're well sorted because we can't see any big pieces. We wouldn't be able to make an indication about rounding because we couldn't see it very well. But if we go back to this image here, so here's our breccia because it's got angular pieces bigger than 2 millimeters. This is our conglomerate because it's got rounded pieces bigger than 2 millimeters. This is our sandstone because they're very small, about 2 millimeters. And of course, if we could see it a little closer in a hand sample, you could feel it. It feels like sandpaper. It's kind of rough. And then this is our mudstone. So the things this tells us are distance from source as a very general rule, and also energy. So what does that mean? It means that it takes more energy to move big pieces. So this had to be a higher energy environment than this. In order to get the really tiny, tiny pieces to settle out, if I have some water that has some velocity, those tiny pieces are floating. They can't get out of the water column. I need the water to almost stop completely, like a lake or a swamp, and then those tiny little pieces will finally settle out and build layers. That's an indication of a very quiet water environment, a very low energy environment. That's where I would get mudstones. But conglomerates and breccias, there's a lot of energy there. And so the size of the pieces can give us some information about that. And so what we want to be able to do is look at our said rock and determine pieces or not pieces, once again as a general rule. And if it's made of pieces, it's considered a clastic sedimentary rock. Sorry about that. And so then we want to evaluate the size and shape of the pieces to give it a name. If it is a chemical where we can't really see pieces, then what we want to do is, oh, I lied to you. These are some more images of the clastic rocks. Let me show you those really fast. So once again, a breccia and a conglomerate, right? Those are those guys. We've got some sandstones here. Look, there's a variety of sandstones based on some of their shapes and compositions. But for us in this class, we're just going to say sandstone is these kind of well-sorted, rounded pieces that are in that range, right? So that's what we care about for sandstones. And then we have these very fine mudstones or shales. Either term is acceptable. And usually these are darker in color is helpful because we really can't see the pieces. And of course they kind of have this very fine layering. So typically those are some clues to help us figure out that very fine-grained or, finely very small class. Try to say something. Small class that make up our mudstone. Okay, and now we're talking about chemicals. So let's say it's not made of pieces of other rocks, so we want to figure out what it is. How do we do that? So for these things, we're do a test. Its composition is key in identifying what type of chemical sedimentary rock you have. So your knowledge of minerals comes back to haunt you. It's helpful now to be able to use some of the tests we use to identify minerals, to identify them in this chemical sedimentary rock, which then we can use to name it and of course figure out where it came from. So there are a bunch. We're just going to focus on a couple, and the main one we'll focus on in this class is carbonates. So limestones mostly. These are rocks that are made of calcium carbonate. That is calcite. And so remember, the test for calcite was it reacts with hydrochloric acid. So if we looked at this rock and we couldn't figure out what it was, it didn't look like it was made of pieces of other rock, we would do a little test by putting this little drop of hydrochloric acid on our sample. If it bubbled, it tells us that it's a limestone. Okay, these are things that come into play when we talk about sinkholes and dissolution and things like that. So definitely a hazard that we'll talk about. And so identifying our chemical sedimentary rocks, we got to do a test, figure out what it's made of. And for carbonates like limestones, the test is it's reacting to hydrochloric acid. Chert, this is a microcrystalline quartz. And so it's usually deposited in these thick layers here, or you can find fragments of them. But how do we figure out what this is? It's certainly not made of pieces. If I thought it was a limestone, I'd put a little drop of hydrochloric acid, no fizz. It's not that. What's another test that I know? Well, in order to identify quartz, we can use the scratch test. A steel nail should not be able to scratch this rock. And so I would grab my steel nail or a steel blade and I would try to scratch it. If it didn't scratch it, I know it was made of quartz. And so a microcrystalline quartz rock is called a chert, right? And that could help me identify what I have. And then finally, for this class, the other chemical rocks are evaporites. And so we've got some gibstone, which is made of the mineral gypsum. It's super soft. You can scratch it with your fingernail is the diagnostic test for that. Or rock salt, which is halite, the mineral, which is cubic if you can see it in its crystal form. It does taste like, I guess I'll have to put an S back in there. It tastes like salt. So, maybe have if you had lab partners, you could make them lick it and tell you it tastes like salt. But these are evaporite minerals, and so they are susceptible to dissolution, much like the limestones. And so knowing something about these rocks can be useful for some of the hazards we'll discuss about, building things on rocks that aren't very strong or have this susceptibility to dissolution. Obviously would be a problem. If part of your land is dissolving, then your surface could collapse or things like that. So this is why these types of chemical sedimentary rocks are important. Okay, so remember, once again, you need a chart like this and able to figure out what you got. So in the lab, you'll have this chart, and we'll look at some images, and we'll try to figure out what type of rocks we have. Our first step, of course, remember, is pieces or not pieces. If they're pieces, evaluate the pieces to figure out what you have. If they're not pieces, you want to do a test. Figure out what it's made of, and the composition will help us identify the sedimentary rock that we have. All right, that was a lot, but I think we're good for the basics of sedimentary rocks, and then we'll do one more for metamorphic rocks, and you'll be good to go.